another new Leetcode problem here. And in this problem, we are given binary tree and we want to determine if the binary tree is balanced or not. Now, simply a balanced binary tree or height balanced binary tree is simply a binary tree in which the difference between the depth of the left subtree and the right subtree is no more than 1. It is that's the definition of a height balanced binary tree. And I've written a solution on my right, but we'll be discussing two different solutions for this problem. The first solution is easier to understand, but it's not the most efficient one, and we'll be optimizing the same problem to make it more optimized and run faster. Okay. So the first solution is on the right, and I've written two functions here, but the function that the program expects is this isBalanced function. It provides us with the root node of the binary tree. And what I'm doing here first is that if the root is none, then it means that there are no elements, and in that case we have to consider them as balanced because there are no left subtree and right subtree. So the depth is 0 on both sides, so it is balanced. We could consider that. Now, if in case we are provided with a valid root node, then we want to find the height of the maximum depth or height of the left subtree and right subtree. That's exactly what I'm doing here. I'm calling a function called find maximum depth, and I am providing it with the left subtree, and then again I'm finding the maximum depth of the right subtree, and this is a function I have defined earlier in the above. You can see there. And after I find the heights, I'm simply finding the difference between those heights, and if the absolute height difference is more than 1, it means that the binary tree provided is not balanced, and exactly I'm returning false here. Right, so if this condition is not satisfied, then it seems that the parent node is balanced, and if the parent node is balanced, that's great. But for a tree to be balanced, the child nodes should also be balanced. So therefore what I'm doing here is that recursively calling isBalanced function, and I'm checking if the left subtree is balanced or not, and I'm also checking if the right subtree is balanced or not, and I'm using an AND statement to check if both left and right subtree are balanced. Parent node is balanced and left subtree is balanced and right subtree is balanced, then the whole binary tree is height balanced. Is that for each node, if I compute the difference between the depth for left and right subtree, then it should be no more than 1. If that is true for each and every node, then the whole tree is balanced. That's the idea, right? Now let's go back to the implementation of finding the maximum depth of a binary tree. This implementation looks a lot familiar because we have actually used this exact implementation to solve another problem, to find the maximum depth of binary tree. And this is a recursive function. As you can see, if the root is none, which means there are no elements, then we are returning the depth to be 0. But if that's not the case, then we are finding the maximum depth of the left subtree and the right subtree, recursively calling the same function. And then we are finding the maximum between those two heights and adding +1. This 1 is added because we want to consider the current node also. And this is the function. And one thing to note here is that both the find max depth and isBalanced functions are recursive functions. In fact, they are nested recursive function, because inside isBalanced we are calling find max depth function, which is itself a recursive function, and isBalanced is again we can see that this function is again called by itself, which means that there's recursion inside recursion, and that is not very efficient at all. Nonetheless, it's still a solution, so it should pass all the test cases just fine, right? And I can submit the solution and should just be fine. You can see the solution took 11 milliseconds and the runtime is slower, but let's let me copy another solution which is more efficient than this one and paste it here. Now right away, the isBalance function does not look recursive at all. In fact, it calls another function called checkBalanced and compute height. Now this function takes in the root and returns back two values. One is boolean value saying if this boolean binary tree is balanced or not. That's what we have returned from the isBalanced function, and it also computes the height of the binary tree. Now if we look at the function, this function is, by the way, recursive, and the first thing we're checking is if the root is none. If root is none, that means there are no nodes there, so the tree must be balanced, obviously, so we're returning true, and the height is 0 because there are simply no nodes here. And then I'm again recursively calling the same function on the left subtree of the same binary tree. Now if the left subtree is not balanced, that's what I have here. If it's not balanced on the left subtree, then obviously I don't have to check the right. It is not balanced, which means that the whole binary tree is not balanced, so I can return false here, and the height doesn't matter anymore for this because it's already not balanced, so we don't care anything about anything else. So yeah, the height we have returned none. Similarly, I can do that for the right subtree. I'm checking if the right subtree is balanced or not, and if it is not balanced, then I can return false, and I don't care about the height in that case. Now if both left subtree and right subtree are balanced, then at the end I have to check if the parent node is balanced or not. To do that, I'm simply computing balanced variable, and what I'm doing here is that checking if the absolute difference between the height of right subtree and left subtree is less than 2. If it's less than 2, then the parent node is also balanced. If it's not, then the parent node is not balanced, and this is something that I'm returning back from this function. I'm also computing the height here, height of the tree, and it is simply the maximum of between the right and left subtree, and we are adding +1 just like earlier to also consider the current node, and we are returning the balanced boolean and the height here. And this function has only one recursion, so it must be faster than previous one. Let's first see if it passes all the test cases. It does, and if we submit the solution, hopefully it's much faster. And it is much faster. It took only 4 milliseconds. Let me submit it again. Sometimes that runtime changes. Yeah, it changes. As you can see, it only took 1 millisecond here. If I run it again, I don't know, for some reason it's different, so it's now 0 millisecond. So it's generally faster than the previous solution we had earlier, which was nested recursion. So yeah, this is better solution. So that's it. Thank you.